Okay, so welcome back. Today we're going to take a little side trip and look into something you might see on the internet. People talking about a circuit. Generally, it's a hobbyist circuit where you can hook up some electronics, and the goal is to measure a transformer, like a switching transformer, like you see here, or maybe even a power transformer. And the goal is to measure the transformer to see if there is a short circuit in the winding of the transformer. And that's a really nice idea. What we're going to do is we're going to kind of dig into that and see what's behind it and look at how the basic concepts of how it works. And you can see here on the scope, we're generating a ringing waveform that we'll talk about, and that's what helps us using the circuit to determine whether the transformer is good or bad, or at least that's the concept. And here is the transformer response. It's an LC circuit. And what I'm going to do is I'm going to simulate a single shorted turn in the transformer, this white wire. I'm going to connect it, and you can see the result is a different waveform. Okay, so without the short circuit, you can see it rings for a longer amount of time, and with the short circuit, it rings for a shorter amount of time. And the testing circuit that we're going to be talking about is called a ring tester. And you can imagine what it does is it looks at the number of rings over a period of time. And with the short circuit, there's going to be fewer rings, as you see here, than without the short circuit, there's going to be more rings over a certain period of time. So we're going to look at what's going on here, what's the basic concept, and at the end of the day, is it going to be something that's useful to you? Now, in this analysis, we're also going to be using a free electronic simulator software. I've talked a lot about it. I've got a series on how to use it. It's called LT Spice. Again, it's free software, and it's a great way to learn about stuff like this and simulate different components and different values very quickly, rather than having to go to the bench and hook it all up and look at the scope. So I encourage you to look at the series on LT Spice. It's called Beginner to Expert. So let's take a look at the basic concepts behind this using LT Spice. So now let's take a look at a very simple circuit and a very basic concept that will help us to understand what this ring tester is supposed to do and how it actually works. And I'm going to start out with this very simple circuit. You can see here I've got a voltage source, and this voltage source is just what's called a step source. It goes from 0 volts and instantly up to 10 volts and stays there. Okay, so it's like a step of voltage. I've got a resistor, a capacitor, and an inductor. And you may be familiar with this. It is what's called an LC oscillator. And the L is the inductance, the C is the capacitance. And in fact, this is an RLC oscillator because it's got a resistor with the capacitor and the inductor. And the way this works is very much like in the real world. If you ring a bell, you take a hammer and hit a bell, what happens? Well, it rings, it oscillates, and over time it decays, and at some point the bell stops ringing, right? It dies out. And that's exactly what this does, but it's in an electrical system instead of a mechanical system. And what happens is the inductor and the capacitor both hold energy. The inductor holds a magnetic field, and the capacitor holds an electric charge. And if you hit them with a pulse of voltage, like we're going to do here, it's very much like hitting a bell. And what happens is the energy in the inductor and in the capacitor gets shared between them. And if there's no resistance, if this resistor was 0 and it's a perfect circuit, the bell would ring forever. And the inductor and the capacitor would exchange energy back and forth and oscillate just like a bell, and it would never stop ringing. It would ring forever. Of course, in the real world, that doesn't happen because you've got resistance in the wires, resistance inside the capacitor, and it's going to dissipate energy and it's going to stop ringing. But the basic concept is it's an LC oscillator where they share energy. So let's take a look at the results of this. If we hit this with a pulse, let's look at the resulting oscillation. So we're going to run this. So now here is our input. This is our step. And as we said, it goes from 0 volts up to 10 volts and stays there. Then what we're going to do is we're going to measure the voltage at this point in the circuit and see what we get. So here is the result. And in blue, we have our input pulse. It goes from 0 up to 10. And in green, we have the voltage across this inductor. And you can see it's oscillating. And it is slowly decaying over time. And that is because of the resistance in this circuit. You hit it with one pulse and it goes and it oscillates. And this type of circuit is used often to generate oscillating waveforms, sine waves. We can see that this resistor, and this is very important, this resistor causes this LC circuit to be damped and decay. Now what we can do is I can change this to 0.1 ohms. So you can see it's oscillating, but it's not being damped as much because there's not as much resistance in the circuit. Now I can go through and I can change this to say 10 ohms. And what do we expect? Well, we expect it to be damped more than before. So I'll rerun it, and here is the result. You can see it's damped very quickly because I've got more resistance, more energy being dissipated in this resistor, watts being lost in this resistor, which causes the energy to be lost in this circuit. It's no longer being stored here, it's being lost in this resistor, so it's being damped. And that is a very important concept that's being utilized here. It's saying that you can basically look at this output waveform and determine how much or relative amount of resistance are in this circuit. And the way you do that is you can say, for example, with 10 ohms in the circuit, I can look at this waveform, and if I can measure the number of peaks above, say, 5 volts, here I've got 1, 2, 3, 4, 5, 6, 7, maybe 8 peaks above 5 volts. But if I change this back to 0.1 ohms, and I look at the number of peaks above 5 volts, you can see it's many, 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 many peaks, and it could go on for a few seconds. So we can use the number of peaks or the number of rings to effectively determine the relative amount of resistance in this circuit. And that is basically what a ring tester does. Now, as a side note, you can calculate the resonant frequency, the frequency of this sine wave that this circuit is ringing at, by taking the inductance value and the capacitance value and filling it into a formula. But basically, you take the L and the C and you go through and you calculate. And it turns out for these values, 0.1 microfarad and 10 millihenries, the resonant frequency is about 5 kilohertz. And we can go in here and we can zoom in and we can check, we can measure one period of this waveform. And if you can see down the bottom, it says 4.96 kilohertz. So it's right on 5 kilohertz. So basically, you can determine a relative amount of resistance in the circuit by measuring the peaks. Now there is one other related but not really important aspect of this RLC circuit, and that is what's called the quality factor or the Q factor. And that is basically just an indication of the relative amount of resistance in this inductive circuit. And as we said before, the amount of resistance affects how quickly the ringing is damped. So a Q factor that is high means there's a lot of inductance relative to the resistance, and a low Q factor means a lot of resistance relative to the inductance, which means that a low Q factor, you're going to expect quicker damping than you are if you have a high Q. So kind of related, but really not that important in this discussion. So now how is that going to help us determine if there is a shorted winding in our transformer? Well, you can see here we've got a very similar circuit to what we were just looking at, but I've replaced the inductor by the switching transformer that we're going to be testing. So I've got the primary winding, which we said is 10 millihenries, and that's just a ballpark. We've got our 0.1 microfarad capacitor. We've got a 0.5 ohm resistor or whatever. That just is representative of the resistance of the winding of this inductor plus the wires and everything else. And we've got this pulse wave coming in. Now, what I've shown here is the primary winding of the switching transformer and two secondary windings. One is a normal winding and one is the shorted turn that we're going to be simulating. And you can see here I've got a 10 millihenry inductance on the primary, 0.05 millihenries on the secondary of this winding. And the shorted turn, I've given it a very, very low inductance of 0.001 millihenries. This is just kind of a ballpark value, but it's a very low inductance. It's only one turn. And I've got here a 0.1 ohm resistor that we can apply to this and see how it impacts the good, what we've called the good winding, the good output voltage, like in an ATX power supply, it might be 12 volts DC coming out. So now this capacitor here is something we're going to add into our tester circuit so that we get the oscillations. Without that capacitor, without us adding that capacitor, you're not going to get oscillations. You may get some based on the internal capacitance of the transformer and so on, but this is a fairly large value that's going to give us a predictable ringing. So we've got the resistance. We've simulated the resistance of the winding in the wires. We've got this, we've added this 0.1 microfarad capacitor, and we've got this switching transformer. But if we apply this short circuit, we are adding a resistance into this RLC circuit, depending on how much resistance we connect here. And the concept is if we add a resistor across here, it will cause the voltage, for example, if we measure this good voltage, it should cause that voltage to decay more than it normally would. And we can use the ring tester to test how many rings it has to get a relative idea. So now let's run this simulation. Again, we're going to put 0 to 10 volt step in here, and we're going to monitor some of these voltages and see what we get. We'll start out with no short-circuited turn on the transformer. Just we're applying a pulse and watching this ring, and we should be able to see that on this good winding output. So let's run this. So here is the voltage measured on this good winding. And you can see it's kind of like we had in the other circuit where it's oscillating and it's probably at 5 kilohertz, and it is slowly decaying over time because of the resistance in this primary. So now what we can do is we can apply this short circuit and see what it does to the good. Now again, keep in mind, this is a test circuit. This isn't what you're going to have in the real world when you're operating your switching transformer, because we've added this capacitor and we've got this step pulse. So this is just a test circuit. So what we're going to do is we're going to connect up this 0.1 ohm resistance of the short-circuited winding. We're going to rerun this. And here is the output of the V good, the voltage out of this good winding. And you can see, as we expected, it gets damped very quickly because we've added a 0.1 ohm resistance into the circuit. So we've got a lot of damping, and that's what the ring tester takes advantage of. Now the number of peaks is diminished quite a bit compared to what we had before. So now that we have a basic conceptual idea of the RLC resonance circuit and the damping that might be introduced by adding a short circuit to a transformer, the next question from an engineering perspective is, so what? Right? Is this something that is really of practical use, or, as you see a lot of on the internet, hobbyist projects that hobbyists think are fun, but in the real world, it's of little practical use. So if you look at this circuit, we have chosen some values of inductance of the transformer winding, capacitance for the resonance circuit, resistance that simulates the resistance of the inductance winding. Also, you've got what's called ESR of the capacitor, equivalent series resistance. So you've got a resistor inside this capacitor. You've got wire resistance that you're simulating. You've also got a voltage here that we've selected 10 volts. We've got, more importantly, a model of a shorted turn, which has a very low resistance. So in order for this to be a practical circuit, you have to step back and say, well, are these good values? If I have a particular switching transformer, is this going to work? Is this something that is going to be indicative? If I apply a pulse through a capacitor and a resistor into my switching transformer and apply a short circuit, is it going to be a viable test to measure the number of pulses above a certain value with and without the short circuit. And that becomes a really important point if you want to figure out if this is going to work. Is it going to work with a certain switching transformer with a certain value of inductance and with a certain short circuit and capacitor value and everything else? So it becomes a very challenging task to figure out whether this concept is going to be of any use in the real world. So what I've done is I've made a list of questions that if you're really going to use this to test short-circuited transformers, here are some questions that I think are really important that you have to answer if you really want this thing to be valuable. How practical is it? First of all, likelihood of transformer failure. If you've been around the electrical engineering world for any amount of time, you are probably aware that transformers are fairly reliable components. It's basically an insulated wire wrapped around an iron core. Not a lot can go wrong with it, and engineers, when they put a transformer in a circuit, they generally provide protective devices. For example, a metal oxide varistor or a diode to prevent back EMF. So there's a lot of protective devices, and at the end of the day, what's the likelihood that a transformer is actually going to fail? As an example, the power company that serves power to your house, they have some very expensive, very large transformers out in the outdoors in what are called substations, and those are exposed to the weather, to lightning strikes and everything else. You shouldn't be surprised to find out that that transformer may have been put in service back in like the 1960s and still operating. Transformers are generally very reliable devices. Now, that's not to say that you won't encounter transformers that are failed either because of the protective equipment that's designed to protect it has failed, or it's just a bad component. Every component at some point is going to fail in its life. Yeah, you can have transformer failures, but is it something that is really likely? And then if it does fail, what is the likely failure mode? And is this ring tester something that is going to detect that? So for example, a high voltage spike, if the protective equipment doesn't protect the transformer, what's going to happen? Well, it's probably going to flash over. It's going to, the insulation is going to fail, and you might have either a temporary or a permanent short circuit. Is this tester going to help you with that? Right? So you got to think about what's the failure mode. And is this tester designed to detect that failure mode? Now, if it does fail, is it worth troubleshooting and replacing? For many people, I think the answer to that is probably no. For example, if your ATX computer power supply fails, is it worth going through and risking the high voltage of the power supply and testing it and troubleshooting and replacing the transformer if indeed it's the transformer? Maybe not. In the commercial industrial world, often they will get technicians coming out that will contact the manufacturer and get a new device rather than taking all the time going through and looking for, a single transformer failure. Now, you may be someone who's got a box of switching transformers and you want to check to see which ones are good and bad. That's fine. But for most people, I think, is it really worth troubleshooting and replacing? The answer may be no. And are other failure symptoms easier and more obvious to detect, right? If you have a spike of voltage that destroys the insulation of the transformer, maybe the output is 0 and you don't need a ring tester. There's more obvious symptoms that you're dealing with. Also, a very important thing, what transformers does it work with? Again, the operation of this RLC circuit depends on the inductance values, the capacitance values, the resistor values. So what transformers, what inductance values will it work with? Does it work with a power transformer that has inductance values in the henries range rather than the millihenries? Is that still going to work? Maybe not. And then what faults does it find? What is it good at finding, and what types of faults won't it find? And you also have to worry about false positives and negatives. Are you going to have a good transformer that you put in the ring tester, and because of these other factors, it maybe says that it's a bad transformer, when in fact it's good. So you really have to investigate this, what it works with, and what is really a good transformer. How many rings for a good transformer and how many rings for a bad transformer. And then, you see a lot of people talking about a single shorted turn. They're simulating one shorted turn. How likely is that? Is that something that you really are going to see? And then does a single shorted turn impact the overall transformer performance? I mean, maybe with one shorted turn, the transformer is going to be like new, and the non-shorted windings might be working fine. So is this really something we have to worry about? And a very important thing is the characteristics of the short-circuited turn or turns. Is it really a low resistance? Is the turn only shorted when high voltage is applied? Maybe it's damaged the insulation, but still it's got some insulation, air insulation, and maybe, in order to recreate that short, you need to apply a high voltage. And then one other thing we talked about before, all the component variables. You have to make sure you're taking into account the equivalent series resistance of the capacitor, the applied voltage, what's the correct applied voltage, what are the short circuit parameters, what's the resistance of the short circuit, and what's the transformer inductance and series resistance. So you can see there's a lot of stuff that you're going to have to work through if you really expect this to be of any use. Personally, after the first 3 or 4 questions, my view is that for me personally, it's of zero use. I've been, like I say, electrical engineer for over 45 years. I can't remember when I've ever had the need to check a transformer winding failure in a switch mode power supply. I've owned many computers over the decades, and it's never been an issue. But again, if maybe you're a repair person and you've got a box of switch mode transformers and you're certain that all of these questions are answered and you know that it's going to be a reliable test, and that's fine. Just these are things to keep in mind from an engineering perspective to determine whether this, at the end of the day, is a useful test. So here's one example. What we're talking about is some of the variations. Instead of a switching transformer, I have changed the inductance of the primary from 10 millihenries to 6 henries. And that 6 henries reflects a 112 volt to 12 volt bench transformer I have. You can see that the actual inductance is much higher for a power transformer. And I've also changed the resistance to reflect the measured ohmic resistance of the winding of this primary, and it's about 20 ohms. And I've left this capacitance at 0.1 microfarads, and I put the same pulse, and up here you can see the resulting ringing, and this is about a 200 hertz. Rather than 5 kilohertz, this is now 200 hertz. So we're talking about a much longer time period for this thing to oscillate. And with this resistance, the 20 ohm resistance, here we are 0.2 seconds, and you can see it slowly decaying. So what we can do is we can now apply the short circuit, the same 0.1 ohms, and rerun it. And you can see the results over the same 0.2 seconds is that, it decays more, but it's not quite as obvious. The question is, are you now going to have a ring tester that operates now within a 0.2 seconds range and takes into account the difference in resistance and inductance? So you can see it can get really complicated, and it's not just a very straightforward, press a button and, 5 LEDs tell you the right answer. No, you really have to do some investigation to come up with the right value. So anyway, that's about it for this. If you like any of these videos, hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Otherwise, take care. Have a really good day. Thanks.